Welcome to enthalpy. If the system is free to change its volume, then the change in internal energy is not equal to the energy transferred as heat. In such a case, some of the energy supplied to the system as heat is returned to the surroundings via expansion work, and du is less than dq. Now the enthalpy H is defined as enthalpy, capital H, is equal to the internal energy plus P times V, plus pressure times volume. Now because U, P, and V are all state functions, that means that H, the enthalpy, must also be a state function. At constant pressure, and if no non-expansion work is done, then an infinitesimal enthalpy change is equal to an infinitesimal heat released by the system. So dH is equal to dQ. For a measurable amount of heat released, then the enthalpy change, delta H, is equal to Q sub P. So now Q sub P is the heat released at constant pressure. So an enthalpy change can be measured using calorimetry, just like we could measure an internal energy change using calorimetry. Now an internal energy change was measured at constant volume. An enthalpy change will be measured at constant pressure. So we're allowing the volume to change. That is, the temperature change of the system can be measured at constant pressure. A calorimeter used at constant pressure is called an isobaric calorimeter. A simple isobaric calorimeter can be constructed using an insulated container open to the atmosphere, for example, a foam coffee cup. For studying combustion reactions, an adiabatic flame calorimeter can be used. In this case, a known quantity of fuel is burned in oxygen inside the glass bulb. So we've got a few tubes, we've got some gas or fuel coming in here, we've got some oxygen coming in here into the glass bulb. We allow that combustion reaction to occur, and as the gas comes out, it then flows around here before flowing out as exhaust, and we capture that heat perhaps in something with a larger heat capacity like a water bath, and then we measure the temperature change of that water bath. So again, the entire apparatus is then submerged in a water bath, and we measure the temperature change of the water bath to allow us to calculate the amount of energy released by the reaction as heat. Alternatively, we could use a bomb calorimeter to measure the internal energy change of that process. The internal energy change can then be converted into an enthalpy change. Now recall that solids and liquids have a small molar volume, and that means that the pressure times the molar volume for a solid or liquid is rather small compared to that for a gas. And this means that the molar enthalpy and molar internal energy are nearly identical for a liquid or a solid. That is, the molar enthalpy, which is equal to the molar internal energy plus pressure times the molar volume, is approximately equal to the molar internal energy because the molar volume is rather small. And this means that if a process only involves liquids or solids, then delta H and delta U are nearly identical. And such a process is accompanied by such a small change in volume that the expansion work done is negligible, and virtually all of the energy supplied as heat remains within the system. The most sophisticated way of measuring an enthalpy change is using a differential scanning calorimeter. So recall that H was equal to U plus PV. So the enthalpy change of an ideal gas can then be represented this way, where we have H, the enthalpy, is equal to U, the internal energy, plus nRT. And this then implies that the change of enthalpy in a reaction that produces or consumes gas is given by this reaction, where we have the enthalpy change, delta H, is equal to the internal energy change, delta U, plus delta Ng, where Ng here is the number of moles of gas. So delta Ng is the change in the number of moles of gas in our system, times R times T. Now the enthalpy increases with temperature, and at constant pressure, then we get this equation, where we have the constant pressure heat capacity, Cp, is equal to the partial derivative of the enthalpy with respect to temperature at constant pressure. And again, this heat capacity is an extensive property. It depends upon how much of our material we have. If we want to get an intensive property instead, we use the molar constant pressure heat capacity, Cp, N, which is the constant pressure heat capacity, Cp, divided by the number of moles N. And at constant pressure for an infinitesimal change in temperature, we have dH, the infinitesimally small change in enthalpy, is equal to Cp times dt. If the constant pressure heat capacity is constant over some measurable temperature range, then we get this equation. So delta H is equal to Cp times delta T. Now, because the enthalpy change is equal to the energy supplied as heat at constant pressure, then we can say Q equals C delta T, with our Q and C being fixed at constant pressure. So the heat supplied at constant pressure is equal to the constant pressure heat capacity times the change in temperature. The heat capacity varies with temperature. So if the temperature range is small, then the variation of heat capacity with temperature can be ignored. If we can't ignore the variation of heat capacity with temperature, then a convenient approximation for the variation of heat capacity is given here, where we have the molar constant pressure heat capacity is equal to A plus B times the temperature plus C divided by the square of the temperature, where A, B, and C are empirical constants and are independent of the temperature. Now, most systems expand when heated at constant pressure, and such systems do work on the surroundings, and thus the temperature increases less than when the heating occurs at constant volume. Furthermore, a smaller change in temperature implies a larger heat capacity, and therefore the constant pressure heat capacity is typically larger than the constant volume heat capacity will be. And the relationship between the two heat capacities is given here for an ideal gas. We have the constant pressure heat capacity minus the constant volume heat capacity is equal to N, the number of moles, times R, the gas constant. So that was enthalpy.